Good morning. Today we start the topic automata-based LTL model checking. And the most important names that are connected with this work is Moshe Vadi, Rice University US, and Pierre Volpert, University of Liège, Belgium. They developed this technique that I'm going to explain today and actually Friday in the mid-80s. And they received several awards for this work. And the key idea is to use automata, in particular Büchi automata, to do LTL model checking. So we are confronted with the following problem, the LTL model checking problem. We are given a finite transition system over some set of atomic propositions. We assume, without loss of generality, that this transition system has no states without outgoing arrows, so there are no terminal states. And we are given an LTL formula over the same set of atomic propositions, AP. And the question is, does my transition system satisfy the LTL formula phi? So the basic idea is that we try to actually show that the transition system violates phi. So, as you remember, with safety properties, we're always looking at the bad prefixes. When I introduced you the algorithm to check omega regular properties, we were taking the Büchi automaton for the complement. So we always look at something which is bad. The same principle applies here. So what we're looking at is trying to find a path, a computation in the transition system that refutes the LTL formula phi. So, stated differently, phi satisfies the negation of the formula. So what's the idea? The basic idea will be the following. We're going to construct algorithmically a non-deterministic Büchi automaton for the negation of the formula that we want to check. So we generate an automaton that accepts all the infinite words excepting not phi. That will be the key idea today. Then we want to search for a path in the transition system that actually satisfies not phi. And that means that actually we are looking for a trace that is accepted by the automaton, because that's the way we constructed the automaton. And the way to do that is actually something we know, because we can do this in a very similar way as we have checked omega regular properties. We construct the product of the transition system and the non-deterministic Büchi automaton for the negation of phi. And we search in this product for a path actually that meets the acceptance condition of this A, of not phi. Good. If we found such a path, then the property is refuted because we have a path satisfying not phi. If we don't find such a path, the property is satisfied. Good, so this is the picture, a finite transition system and LTL formula. This is the question which is at stake, and we would like to say yes or no. And the way to do that is we're going to construct algorithmically from the LTL formula phi an NBA, and this is the most important thing, of not phi. Now, one of the things you could ask is something like, why don't you take phi, why don't you take the Büchi automaton for phi and negate the automaton? Yeah? There's a very high complexity. Yeah? So that's not the way we're going to do it. Yeah? That would in principle be possible. It's effective, but it's not very efficient. So therefore it's much easier to take the formula and put a negation in front of it. How easy is that? I mean, you just get a constant extra, one symbol more, and then you construct the NBA for this. So that's the reason why we do the negation of the formula and construct an NBA for this. Good, and then the LTL model checking is something we're all already familiar with, because now we take the product of the transition system and this non-deterministic Büchi automaton for not phi, and we're going to check whether from some point on you cannot reach a final state anymore. Because this means you can only reach a final state in the bad automaton A finitely often, and therefore we don't accept. Okay, and you can also find an error indication as we have seen already. Good, so just to show you the similarity between the safety properties and the LTL formulas quite quickly on this slide. In the safety properties we were constructing an NFA for the bad prefixes, which were finite words. Now we take an NBA for the bad behaviors, which are the, let's say, the words accepting not phi. Here we were checking whether the transition system has no finite traces, which are bad prefixes. Now we're going to check very similarly whether the transition system has no infinite traces, which are accepted by the bad behavior automaton. Then we're going to check here for safety properties in invariant. And as we know, there we were checking a persistence property. Is it the case that from some point on always, you never visit an accepting state anymore? Good. The error indication here is a finite path. The error indication here is a prefix of a finite path, of an infinite path, such that the trace of this path is actually accepted by the bad behavior automaton. Good. So here I think is again the repeat. I'm going to skip this. This is already clear, I think. So the main question which is today at stake, how to get from an LTL formula to a non-deterministic Bugge automaton. So this is the theorem, and this is the famous Vardy-Volpaire theorem, I think 86, that says for each LTL formula phi over some set of atomic propositions, there does exist a non-deterministic Bugge automaton over the alphabet 2 to the power ap. This automaton accepts sets, sequences of sets of atomic propositions, so the alphabet is 2 to the power ap, such that, first, this automaton is correct. That means the set of infinite words accepted by this automaton is the set of infinite words or the infinite traces that satisfy phi. And moreover, as we're going to see, the size of this automaton is exponential in the size of the formula. In one of the next lectures, I'm going to also discuss the hardness of LTL model checking. We're going to see it's p-space complete. So this exponential blow-up is actually unavoidable. Okay, so this is the theorem that is at stake. I'm trying to explain you what's the construction, first the intuition behind the construction, then the construction, an example on the blackboard, and if time permits, I also want to give you at least some idea of the proof. Good. So the intuition. The intuition is the following. We're going to interpret basically NBAs over LTL formulas. So if you look at this automaton, what's the language that this automaton accepts? Well, at some point you need to have a not A and then you accept anything. So this means something like next not A. It's next because you first do this transition where you accept every basically word, every set of atomic proposition, but then you should have a not A. So this looks like an automaton that corresponds to the formula next not A. Good. Similar like this is one automaton with two initial states. So this can accept an A or it can accept a B. So the language accepted by this is the set of infinite traces that satisfy the LTL formula A or B. Good. What about this? There's about the atomic propositions A and B. We have to visit this state infinitely often. You can only do this if you have always A. So the language of this automaton corresponds to the LTL formula, the words of box A. Okay, so these examples show you already that there is a similarity between LTL formulas and Bugge automata. I think there are more examples here. So this is something like here you do an A, you have to visit this infinitely often. So this is also something like that you basically do infinitely often an A. It's infinitely often because you can also go back and then do an A. So this is something like infinitely often A. This is an automaton where we have to go through this state infinitely often. How do we get there? Well, we get there by doing a B. Well, not A or a B going here, but so that means that if we have done an A moving here, okay, then a couple of times not B, but at some point we have to get a B. Then we can do another A moving there, then we again can cycle around a bit, but at some point we need to respond to this A by a B. So this looks something like box A implies eventually B, and that's exactly that we're going to see. So this accepts, for instance, the word the empty set omega. Why? Because you can take this loop infinitely often. That satisfies not A, the empty set. So that's all fine. And it also satisfies, for instance, AB, where you just alternate without taking the self loop in Q1 any times. And as I already was hinting at, you get something like box A implies eventually B. Good. So intuitively, I hope it's clear that there is a connection between Büchi automata on the one hand side and an LTL formula on the other hand. Why do we need non-deterministic Büchi automata and not deterministic Büchi automata? Well, you have things like this, where there is non-determinism in Q0. So here, either if an A is the next symbol, you can either take the self loop or you can move with A to Q1. And this is accepting if you take this infinitely often. So this automaton accepts if eventually box A. From some point on, only A's. The question is, when do we get only A's? And this is why we need this guessing in Q0. And well, that's what I just said. And of course, you have, if you put A omega and you always take the self loop, this of course is a not accepting run. But this of course also has infinitely many runs that are accepting on this word. Because on any position here in Q0, you can decide to Q1 and then you will accept. Good. Okay, so for LTL, we definitely also need non-deterministic Büchi automata because we have seen that you cannot express this language by a deterministic Büchi automaton, right? They were strictly less expressive. Good. So one slide that safety properties are easily captured by NBAs. So if I have an NFA for the language of all the bad prefixes, then the set of infinite words of A is basically the complement of the safety property, which are all infinite words which are not in the safety property. So if you have something like never A twice in a row, then this is an automaton that says, okay, if I have twice in an A in a row, and then I accept. And that means that something like, it's always the case that if I have an A, then the next position should have a not A. You have to be a bit careful if LA is the length of minimal bad prefixes, but if the language of all bad prefixes, then this trick simply works. Good, so here is the automaton, the Büchi automaton that exactly is this never A twice in a row. Good. I think that's not that much of importance. What is important is this construction, how to get from the LTL formula to an NBA. Okay, so the step is first negate and then to construct the Büchi automaton. Good. I'm going to skip this. I don't know why there's many slides about this. Genau, exactly. So this is what I would like to show. For every LTL formula, there is an NBA such that the set of infinite words accepted by this automaton is the set of words satisfying phi. Good. So this is the construction I'm going to present. Actually, there are many different constructions in the literature. I'm going to present the original one by Vadi Wolper. So the idea is that we go from an LTL formula phi to this NBA, and the construction is via a GNBA. So actually what I'm going to show today is how to get from an LTL formula to a generalized non-deterministic Büchi automaton satisfying basically the formula phi. What was the difference between an NBA and a GNBA? They are equally expressive, both omega regular properties, omega regular languages, but this has a set of sets of accepting states. This has one set of accepting states. But we have seen a construction to go from a GNBA to a Büchi automaton. If this one has k acceptance sets, we can make k copies and transform it to an NBA. Yeah, so if we have explained this step, then we can use the standard procedure to go from a generalized Büchi automaton to a non-deterministic Büchi automaton. So I'm going to concentrate on this first step, going from an LTL formula to a GNBA. Good, so the intuition is the following. We're going to encode the semantics of all the operators in LTL that occur in some input formula phi by using the components of the GNBA. So the states, the transitions, and the acceptance condition. So intuitively this works as follows. So you have the propositional logical formulas negation, conjunction, disjunction, and so forth. We have the next operator and we have the until operator. We know that eventually and box can be expressed in those things, so let's concentrate on the basic operators. So how are we going to encode this? The propositional logical things we are going to encode in the states. And how are we going to do that? We're going to label the states with sets of atomic propositions, which are the atomic propositions that are valid in those states. So if I'm saying A and B, then if the state satisfies A and B, I'm going to label that states with A and B. Next, we're going to cover in the transition relation. This is intuitively, I think, also clear because next says something about what is in the next state. So you encode this in the transition relation. The until is actually encoded in the transition relation, but using the expansion law that we have discussed before. So this was the expansion law, phi 1 until phi 2, if and only if phi 2 holds in the current state, or if that's not the case, phi 1 holds in the current state, but then from the next state on the until formula should hold. So we're going to encode this as follows. Phi 1 and phi 2, psi 1 and psi 2, they are encoded in the states because they say something about what should be true now. And this next is, like this next, we're going to encode in the transition relation. Okay, because this says something about what should be true in the next state of the automaton. Good. And then we need to be clear that we have a least fixed point. Remember, this expansion law has several solutions. We have seen at least two of them, until and the weak until. If we only take this into account, then we are not ensuring that we get the right fixed point. So how do we get the least fixed point? Intuitively speaking, we are going to ensure this by putting the right acceptance condition in the automaton. Okay, so this is the intuition behind the construction. Good. So this is at stake, an LTL formula, and we want to construct such a generalized non-deterministic Büchi automaton. Good. So the states are certain subformulas of phi. So we're going to take phi, just look at the syntax, we're going to look at all its subformulas and actually all its negations, and then we're going to take subsets thereof. But those subsets need to fulfill certain properties, that's why I put certain sets. You can imagine that if I have A in a set, then I should not have not A in the same set. That logically doesn't make too much of sense, right? And there are more of those kind of conditions, as we're going to see. And the idea is that every word, so every, let's say, trace A0, A1, A2, that is, that satisfies phi, that can be basically, if we want this automaton to be correct, it means that this automaton needs to have an accepting run for this input word, because this input word satisfies phi. So the idea is that we're going to construct, well, intuitively speaking, an accepting run B0, B2 in the automaton. And the way to do that intuitively is as follows. So take such a trace that satisfies phi. Now we're going to basically construct, and that's part of the construction in the automaton, an accepting run for this word. Now, this is needed because the automaton needs to accept all the words satisfying phi. So how are we going to do this? We're going to take those B's, which are basically what we're going to see. They are formulas which are part of the closure of phi, and the closure of phi, as I'm going to introduce, is a set of subformulas of phi, such that, starting from the position I, notice here there's I, psi holds. So we're going to take phi, we're going to look at all the subformulas, and then we're going to label these things with these subformulas. So the set of subformulas and their negations. I think there's an example here. A until not A and B. That's phi. Then take this as a run. So this is my example sigma. So this is A0, A1, A2, etc. Good. Let's check. This should satisfy phi. That's at least the claim. So A should hold until at some position we get not A and B, which is here. Good. What's now the intuition? For this we need to get an accepting run, because this word is satisfying phi. So we're going to map in the construction every of those sets of atomic propositions to states in the automaton. So the B's will be the states in my generalized Buchje automaton. And those states will actually be subsets of formulas. So the first thing we're going to do, we're going to take this formula, we're going to look at all the subformulas. So A is a subformula, so therefore we get A, and we also put its negation there, not A. B is another subformula, so we take B and its negation, not B. Then we take not A and B, I just abbreviate this as psi, so that this formula is there, plus its negation, so not this formula. And then the whole formula is also a subformula of itself, so we take the whole formula plus its negation. Yeah, so intuitively speaking, I mean this will be the closure. It's the set of subformulas of phi plus all their negations. And now we can choose the BI's as being subsets of this set. Okay? And these subsets need to fulfill certain conditions. For instance, if I select A, I should not select not A. Yeah? If I select A, if I select not A and I select B, then I should also select not A and B, because that's logically then also true. So these kind of constraints will be imposed on which subsets I am allowed to select. So here as an example, for this is a set which I just put here as a column. So this could be, for instance, the state where you pick not A, not B. Now if A and not B, then this formula is false, right? So that means that I take not the negation of, you take the negation of this formula. A and not B, that means that this formula is true, right? Because A holds until, you have that A is currently true, and this formula is not true, so you're on the way to satisfy phi. That's the idea here. So at some point in the future, you hope to establish phi. That's why I labeled this state with phi. The next A, could label with the same thing. I get a set AB. So now I label this with, of course, with A and B. Now I have to look at this formula. This formula is still false, so I put not psi, and I still put phi because I still have the possibility to establish phi somewhere in the future. And there is B. Of course, A does not hold here, B holds. Now you have not A and B, which becomes true. So I have no choice, I have to put psi there. And this formula holds because the right-hand side of this formula, not A and B, holds. So here actually I have established phi. Yeah. Good. For empty set, of course A and B, neither of them are there. Then psi is not true, so I put not psi there. And actually you cannot establish phi anymore, and that means that not phi holds. Why can I not establish phi anymore? Because neither A holds nor not A and B holds. Yeah? Good. I hope you get some idea about why we pick the subsets that we are picking. Good. So, closure. What's the closure? We take an LTL formula, we look at all its subformulas. What's the closure? The union of all the subformulas plus their negations. Good. I like to do a running example where I do the whole construction, so maybe we take this formula as a starting point. There are more examples on the slide, but let's just take this example. So I take phi, which actually is an old exam exercise, next A until A and not next A. Okay, suppose this is my LTL formula. So the first thing is that we want to construct the closure of phi. The closure of phi contains all the subformulas. Well, A is a subformula, definitely, and we take the negation, so not A is a subformula. Then we have that next A is a subformula here, so I take the negation, which by accident is already there, but okay. Then I take this subformula, right? So I can take this subformula, which is already there, plus its negation, this, but I'm allowed to simplify this. So the double negation can be done, and we have already these elements, so I don't have to add anything. Good. What else do we have to take? We have to take A and next A, the left thing, plus its negation. This is a small next A. And then we have to take this subformula, A and next, not next A, and its negation. And then we have the whole formula plus its negation. So this is the closure of this formula. Good. There is another example on the slide, but I skipped this. I tried to skip to stick to the following thing. Now the next thing is in the procedure. So the next thing is select certain subsets of the closure of phi. And the idea is that they will be the states of our GNBA. Yeah? Good. So we start from this set over here, and now we're going to pick certain subsets. So what does it mean, certain subsets? These certain subsets need to satisfy certain constraints, and we call those certain subsets elementary sets. By the way, how many subsets can I construct from a set? 2 to the power. Here is the exponential blowup. Exactly here. Yeah? We have this set. You can prove actually that the size of this set is somewhat linear in the size of the original formula. Yeah? But this is where the blowup comes, because I pick subsets, and they're exponentially many. Yeah. What does that mean? I get exponentially many states in the worst case. So this automaton may be huge. Good. Okay, what are the conditions that these sets have to satisfy? These are listed on this slide. So it says, okay, pick this closure. So pick this set. Now we're going to pick subsets, but only the ones which are satisfying certain constraints. What are the constraints? First, the constraint says B, so the set we're going to select, must be maximally consistent with respect to propositional logic. Good, that's a whole mouthful. What does that mean? Okay, it means the following. If you have a formula psi, or you have a formula conjunction that belongs to the closure, then the following, I think, three natural conditions hold. Psi does not belong to B if and only if not psi does belong to B. Seems logical, right? So that means that if you don't select psi, you should select not psi. Okay? Good. Then, if psi1 and psi2 belongs to the set, this can only be the case, so if and only if both the conjuncts are in the set. Yeah. And you should read this from left to right as well as from right to left. So if you have both conjuncts in the set, the obligation is you also should put the conjunction in there. Which conjunctions? Well, only the conjunctions which are part of this closure. Yeah, so you cannot build arbitrarily conjunctions, only the ones for the property that you're interested in, for phi. The last thing says, if true is a member in the closure, this implies that true belongs to B. How do I get true in the closure? If you have something like eventually phi, which is equivalent to true until thing, and then you have true as a subformula. Yeah? Good. So I think those three seem to be reasonable. Now the last two. It needs to be locally consistent with respect to until. What does that mean? If an until formula is part of the closure, so if there is some until formula here, which is the case because phi is an until formula, and not phi, by the way, is also an until formula, then the following should hold. If the until formula, if you have selected the until formula in your set, but psi2 is not in the set, Yeah? So that means the right-hand side of the until is not there. Then you are obliged to put the left there. And the intuition is that basically you're saying, okay, suppose that my current state will be labeled with this until. That means I have selected the until formula. Then either the until formula has to be true now, right? Or there is a chance to get it true somewhere in the future. Well, if it's not true now, because psi2 is not in the current set, then there needs to be a chance to get it true somewhat later, and that means that the psi1 needs to be there. Yeah, because if neither psi1 nor psi2 would be there, then there is no chance to make this until formula valid sometime in the future. Okay, good. Last condition, if the right-hand side of the until formula, psi2, if you have selected this, then also you should select the until formula. Intuition, if psi2 holds now, then also psi1 until psi2 holds now. Yeah, first part of the expansion law. Good. Okay, so let's do this for this example. So what I'm going to do is we're going to build the elementary sets. So I'm going to be the elementary sets. For this formula that we just had, phi, which was A and next A until A and not next A. Good. Okay, the way I typically do this is by means of a table. And this is the way you can draw it. So we look at the closure. Yeah? So what are the possibilities we have? Good, so the possibilities is either we select an A or not. We have to select not A. So I'm basically looking at all the positive formulas. I look at this thing, A and next A. Then I look at A and not next A. Yeah, and then there is one formula left, which is phi. Okay? So here we have those columns. Why do I not take all the elements? Because I know the first rule says psi is not in B if and only if not psi is there. So if in this table I'm going to put a 0, for instance, which means I'm not selecting A, it means I have selected not A. Yeah? Of course you can make the table bigger, but this is implicit, right? So notice that all their negations are implicit. Good. So now let's construct a first set. And the first set could be, let's not select A. Let's not select not A. How do I know this? But I don't know. I just decide to not select them. Yeah? I just try in some sense. So it means I have selected not A and I have selected negation of this formula. Yeah, that is what this means, right? So what should I select here? Do I have any choice? No, I have no choice because this formula will be false. Why is this false? Well, look at this formula. I only can have a conjunction if and only if both its conjuncts are part of the set. Well, A should hold and next A should hold, while neither of them does hold. So therefore I'm obliged to put a 0 there. I have no choice. Here I had a choice. And we're going to vary this choice. Here I don't have any choice now. And actually this is now also the case here. I have no choice. Yeah? For the same rule, the same reason, I have not picked A. If I have not picked A, this conjunction is false. Yeah? So this is just propositional logic. Yeah? So now the last thing. What should I put in the last column? This is an until formula, right? Because it's the whole formula. So we have to look at those two rules. Yeah? What do those two rules tell us? Okay. If psi2 is in B, what is psi2? Well, there's A and next A. So this is this. You know, this is psi2. Maybe I'll write this down. So this is, in my case, phi1. This is phi2. And we have a formula of the form phi1 until phi2. Phi2 is not true. So the last rule, right, is not applicable. Yeah? What about this rule? If I pick it and I do not have this, then phi1 must be there. So the other choice I have, so the last rule tells us, okay, I'm not obliged to put the until there, so I'm not obliged to put a 1 there. What does this say? Well, if I put a 1 there and psi2 is not there, which is this 0, then I'm obliged to put phi1 in there. What is phi1? Well, phi1 is this column, but this is a 0. That means I'm obliged to put a 0. No choice. Agree? No, that's true. So this is interpreted as follows. So you're right. Suppose I label the states with, so suppose I select this formula. Suppose I did not select this formula. Then the idea is that this will be a state in my automaton, right? So if I label this state, if this until formula would be part of my state, this would not be part of the state, which means it's not currently true, then there is only one way to establish the until formula, namely that now at the current state, psi1 needs to be true. Yeah? So you're absolutely right. I cannot conclude locally in my state whether the until formula is true, but it might be the case that somewhere later, yeah, after doing a couple of transitions in my automaton, I can still, so there is still a chance to make the until formula true. That's the way to read this. Yeah? Good. Did everybody understand why I had to put a 0 there? No choice. Yeah, so I choose the first two in this line. All the rest follows from the first choices I make. Now, of course, I can vary this choice. So let's do a B1. So the B1 says, for instance, doesn't take this, but it takes this. What would change? Okay, what about this? Well, both conjuncts need to be fulfilled, which is not the case because A is not true. So this now has to be a 0. Same here. You need to establish this A in order to get the conjunction. Well, A has not been selected, so this needs to be a 0. Okay? Good. So the question is what to put here. Same reasoning as before. So we're going to look at phi1 and phi2. It's actually not so difficult because it's exactly the same scenario as we had here. These are the only two cases I have to consider to decide whether I put a 1 here or not. Yeah, because if you look at the last two rules, the only things which are important are those things that actually the subformulas of the until. Well, here is the left subformula, there is the right subformula. If the conclusion was here I put a 0, the conclusion now will be exactly the same. No mercy. So 0. Yeah. So for instance, you see already that if I would put a 1 here, I would violate one of the constraints and this would not be an elementary set, right? Yeah, so I only give you the ones that are elementary sets. Yeah. How many sets do we have? Well, we have 1, 2, 3, 4, 5 subformulas. We have the choice to pick one of the subformulas or not, so potentially we have 2 to the power 5 options. So this table could potentially be big. Potentially. Because you need to fulfill all the conditions, and that rules out many possibilities. Yeah? Good. Okay, B2. I pick this, and then I decide not to pick this. Okay? What do we get here? What should I put here? 0. What should I put there? 1, 0. I hear different opinions. So we have to A holds, right? And it's not the case that next A holds. That means there must be a 0 here. Yeah? Which is the case, so I get a 1 here. Agree? Good. So now what do we have to put in the last column? Okay, we cannot just copy the first two because it's a different situation. We have a 0 and a 1. Good. Okay, so just check the two rules. It says the last rule says if phi 2 is in B, so if here I put a 1, then I must put a 1 there. So no choice, there must be a 1 here. Yeah? By I, second item. Yeah, I hope you see how I construct this table. Standard question in the exam, some LTL formula where you have to construct this automaton. Now we're only here by constructing the states, right? We did not yet consider the transitions and so on, but yeah.
Could you simplify the rule for the until formula until it behaves like instructions? So if I see psi 1 until psi 2, it behaves exactly like psi 1 or psi 2.
You want to combine the two rules, right?
Yes.
Yeah, I think this is possible, but then you have to do some juggling with the formulas. But yeah, I think this is possible. I prefer to make them separate. I think it's a little bit simpler. But B3. Good. So you have seen that once I have fixed those, I have no choices there, right? So I don't have to consider this again. Now I can consider something like 1, 1. Good. A and not A. So and then hope I clear it here. I get a 1. Yeah. What do I get in this column? A 0, right? Because there needs to be a 0. It's not the case, so here is a 0. Now the question is what to put there. Good. So let's see what to put there. So we need to fulfill those constraints. Right? So what can we do? The first says if the last rule says if phi 2 is in B. That means if there would be a 1 in this column, but this is not the case. So the second item of double I is not applicable. So let's select the first one. The first one says if I would put a 1 in the column and psi 2 is not there, which is the case, then phi 1 must be there, and that's the case, so I can put a 1 here. Yeah. But it says the premise, if I put the until formula there, yeah, if I put a 1 here, and here is a 0, then there must be a 1. What about not putting a 1 here? The rule says if I select it, then something should hold. But the rule is also true if I don't select it. Agree? Yeah? So actually I could have chosen a 0 here as well. Yeah? So this is a choice. Yeah? And actually I also have a B4 where all the items are the same except for the last column, because there I can put a 0. Yeah? This is important that you understand that this last rule gives you some freedom. Yeah? And really the way to read this is, if I would put a 1 here, then there are certain obligations to fulfill. If, however, I put a 0 there, and we have already seen, if I put a 0 there, the only thing I need to check is whether the last item holds, but we already have seen that this doesn't hold. So therefore I can put a 0 there. This is all, so we get 5 elementary sets. What does that mean? I get a Büchi automaton with 5 states. Every elementary set will be a state of my automaton. Good. Any questions about this construction? No? Crystal clear to everybody?
I'm not very sure about the B2. How we could be sure about doing the last of the one?
You mean those two?
One before.
This one?
This one, yes.
This one, okay? Here is a 1, right?
We applied the second rule and then, yeah.
This is here we had a 1, we had no choice, right? Because of A holds and not this one. So we have to get a 1 there. Now you look at the last rule of II. This rule, this says if the right-hand side of an until formula has been selected, this is the right-hand side, right? If there is a 1 there, I have the obligation to put a 1 there. And that means in this case, I do not have any choice. Yeah, so as soon as there is a 1 in this column, I don't have any choice here. I have to put a 1. If there is a 0 here and a 1 there, then there is a possibility to be flexible. Yeah? Other questions? Good. Okay, there are more examples on the slides. I prefer to skip this. I prefer to keep to the running example. The slides are available, so there are more examples that you can check in the thing. Good. Okay. So now we have seen how to build the states. What about the rest of the automaton? Good. So here is the definition of the GNBA. So the GNBA has a finite set of states. As we are going to see, those are the B's in my table. Those are the elementary sets. This is the alphabet of the automaton. We have a transition function, we have a set of initial states, and we have a set of accepting states. Yeah, it's a GNBA. Good. The first thing, the state space. Well, that's what I just already explained. What is the state space? They are all the elementary sets of the input formula phi. Yeah. So in my table, these things, these are the states of the GNBA G corresponding to the formula phi. Good. Next. The initial states are those states that include the original formula. So what are the initial states? The initial states are those states where there is a 1 in the last column. Yeah, because this was my input form. So this is going to be an initial state. Well, maybe not do this. This is an initial state, right? And B3 will be an initial state. So in my case, I get Q0, which will be B2 and B3. Good. Next topic. The transition relation, the hardest part. So what do? We want to make transitions from a state. So I pick a B. A B is a state, right? And I pick the next input symbol. What is an input symbol? My alphabet is 2 to the power AP. So this is a set of atomic propositions. This is a set of formulas, right? This is one of the B's I just have constructed here, and this is a set of atomic propositions. And now it says if the set of atomic propositions is different from the set of atomic propositions in the current state, then there is no transition outgoing from B labeled with A. the way to see this, or intuitively this means, we have labeled B. These were the labels. Everywhere where is a put a 1, that is a label. Yeah? Now you look at which atomic propositions are true in the current state. Yeah, this means if not all the atomic propositions of A are currently true, I cannot move if the next input symbol will be A. If A, however, equals the set of atomic propositions in the current state, then it's a non-deterministic automaton. We go from B by the next input symbol A to a set. Now, how do we determine this set? So the B primes are the successor states, okay? Now the successor states are determined as follows. As I was already anticipating, that had something to do with next and with the expansion law, so also with until. The first thing says the following: if the current state is labeled with next something, this must be true if and only if the next state B prime is labeled with psi. Okay? Second rule, if the current state is labeled with the until formula, so if you have decided to put a 1 in the column of an until formula, then psi 2 must be true in the current state, or psi 1 must be true. Actually, those two constraints are already fulfilled by the elementary sets, but the most important point is here. Then psi 1 until psi 2 must also be true, or must be labeled in the next state. Yeah? B prime is the next state. Yeah? So here was your question that you want to establish. Suppose that this formula is there, but only psi 1 and not psi 2. Then you still have a chance to fulfill it, and the chance is basically passed on to your successor, yeah? Your next state, that then needs to fulfill the until formula. Good. Okay, so let's try to construct some transitions. So suppose I take B3 and I take as input set A. Okay, so this is the capital A on the slide, this is the capital B on the slide. This will be a set of states. The question is, what states are in this set? Good. So these are all B prime, such that, yeah, if, for instance, if a next formula is in B, so look at B3. We look at B3. Where is B3? B3 is here. Yeah, so I'm considering this state at the moment. We have to check, is there a next formula in this thing? Yeah. So we just look at the columns and we see, hey, there is a next formula. We don't have to look at the conjunctions, right? We only have to look at this. There is next A in here. So the only next formula that we have to consider is next A. So next A belongs to B3. And now look at the definition, if and only if, yeah, A, this part, belongs to B prime. Okay? So this says the possible successors need to be labeled at least, there are two conditions, right? One for next, one for until, but if A must be in B prime. So the only possible choices is that B prime is an element of the following set, namely all the elements where there is a 1 in the first column. Yeah, A needs to be there. A is there in B2, B3, and B4. So according to this first rule, the choice is already reduced to B2, B3, and B4. But there are other constraints to check, namely the until. Yeah? So this is the first constraint. And I need to check the second constraint. Is there an until formula in B? Now go back to the definition of the sets. Is there an until formula in B3? Yes, there is, because there is a 1 here, and this is an until formula. Yeah? Good. So there is an until formula, namely the whole formula. Yeah, we have that phi belongs to B3. Phi was the entire formula. That means that if and only if, well, phi 2 belongs to B3, or so that means if and only if phi 1 belongs to B3, yeah, or phi 2 belongs to B3, and now it comes, the until formula must also be part, so phi itself must also be part of B prime. Yeah? The only thing we need to check, is this already satisfied by this? That means there is no further obligation to B prime. Yeah, because then because of the disjunction the formula is satisfied. So we have to go back to B3. What is B3? B3 says, there is a 0 here. So this is not the case. Yeah? So this is not fulfilled by looking at B3. So this is not true. But we have that phi 2 does not belong to B3. So that means we have to fulfill this part. We don't need to check this because this has been already checked when we constructed B itself, B3 itself, the elementary set. So the only thing we need to fulfill, phi must be in B prime. So what are the possible successors? That means that B prime must be a member of the set of states that are labeled with phi. What is the set of states? What are the states labeled with phi? Where did I put a phi in the last column? It's B2 and B3, but not B4. Yeah? So this says that this belongs to B2 and B3. Yeah, definitely. Okay, so I have two constraints. This constraint, right? And this constraint. You have to fulfill both. So what do we get? Thus, delta B3 on the singleton set A will be the set B2, B3. I hope you see that in this way you can very systematically check which transitions are in your automaton. One remark about negations. Before I make the remark, are there any questions on this part? No? Doesn't seem to be the case. Okay. And this you have to do for all transitions. What about this? What is the delta of B3 with the empty set? The set of atomic propositions is only A, right? So we have only that AP is just a singleton set. So now I have taken the whole set. I could also have taken empty set. What are the possible next state of the empty set? Empty set. Yeah. Why? Now, this is the rule that says if A, because empty set is different from B3 intersected with A, because that's the singleton set A. Yeah? So there are no outgoing arrows with empty set. One remark about negation, because that sometimes leads to confusion. So actually you can show the following property, which is maybe an open door, but nonetheless I would like to, if you have a formula of this form in the closure of phi, then the following holds: not next psi belongs to B, if and only if psi does not belong to B prime. So on my slide, now, the first line in this boxed frame says next psi in B if and only if psi does in B prime. Actually, you can also have this. Yeah, so that means if not next thing is in B, if and only if psi does not belong in B prime. So how to show this? This has to do with properties of elementary sets. So let's do this. So let not next psi in B by logical consistency of elementary sets, it follows that not next psi belongs not to B. Yeah. If this is in B, its negation is not in B. Yeah. So that means next psi belongs to B. Since next psi in B, if and only if psi in B prime, it follows not. Yes. It follows that psi is not in B prime. The other way around. Let psi not in B prime, since next psi belongs to B if and only if psi belongs to B prime, it follows that this thing is not there. By maximality, maximality says either the formula is there or its negation. Yeah, it follows that if this is not there, that the negation of this formula belongs to B. Yeah. Why do we need this lemma or this proposition? Well, go back to our running example. Look at the state that has not a next formula in here. So for instance, it has a next A and has a 0 there. Yeah. That means the negation of this formula is there, and then yeah, this is applicable. The negation of things there if and only if that formula is not there. Yeah. So for instance, this is needed to establish the successors of, for instance, I don't know what, B2. B2 is labeled with A, so take the successors with respect to A. Yeah. Why is it needed there? Because there is a 0 here. The 0 stands for the next. Yeah, so the first constraint, so this will be a B prime. So it's a set of B primes, if you want, such that B prime satisfies, again, two constraints. The first constraint says, okay, look at B2. There is not a next formula, there is not next A belongs to B2. Thanks to this property, we are now able to conclude this is true if and only if, yeah, psi, so that means A belongs not to B prime. So that means in our case that B prime must be a member of the sets where A is not there, which is B0 and B1. Yeah? I hope you see I was not able to conclude this by just the two rules in this box thing. I need this proposition. A similar proposition holds for the until formula, which I'm not going to give here, but that's, if you apply this in exercises, you will be able to also to see that you also can apply this. And then of course there is a second rule for the until, which I don't have immediately available, but we, to the sake of completeness, we can fulfill this. So what was the second constraint? So I'm still about considering this, right? So 2, what other constraints does B prime have to fulfill? Well, we have to check the until formula. We are considering B2. B2 is an until formula included in this set. Yes, it is. So we have that phi belongs to B2. If and only if, well, either phi 2 belongs to B2 or something, and then something about B prime. So let's check about phi 2. We are considering B2. Phi 2 is there. Yeah? That means no further obligations to B prime. Yeah? If and only if, and this is true. Yeah, and this is now vacuously true. So no further constraints on B prime. This is the same as saying B prime can be any state. So the only constraint we have to fulfill is B0, B1. So we can conclude delta B2 with A is B0, B1. Good. I do this on the purpose that you understand the steps to make those transitions. Okay, any questions on this? Good. So let's, after all this work, draw the automaton. So if you continue this, what you get is something like this. So let me try to see. We have B3, B5, B1. Let me first draw what we already know, and then I get to the rest, B4. So what do we know? We know that the initial states are B2 and B3, which is a bit surprising to me. Because that's what, because I labeled those damn things in a different way. Good, okay, then we draw a new picture. Yeah. That's okay. So these were the initial states. Sorry for the relabeling. So these are the states. So what do we know? We have seen that there are transitions from B2 with singleton set A to B0 and B1. So there is an A transition going here, and I labeled the transitions with a logical formula, right? This A is denoting the singleton set A as before, and there is a transition here. That's what we just have seen on this board. What else did we conclude? We concluded that from B3 there were some A transitions. Let's just draw the diagram. I mean, here is an empty set. Here is an empty set. Go back with empty set. Here I get an A. Here I get an A. I think this was the other one that I constructed. This is the empty set. And this is an empty set. And this is an A. I think the ones that I did on the blackboard was this one, this one, and that one. These were the calculations we did. Yeah. The other ones, yeah, I mean, you have to do the calculations yourself, but it's systematically going via the same way. Good. So what is left? Acceptance conditions. Good. So let's look at the definition for the acceptance conditions. Now, what's the acceptance condition? It's a generalized Büchi automaton, so it's a set of sets of accepting states. Yeah? So what is F? F is something of the form F1 blah 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 Fk. What is K? K is the number of until subformulas in my original formulas. So here it is written down normally. So the acceptance set is a set containing a set of states. Yeah, so it's a set of sets. And we have a set for every until formula in the closure. So intuitively speaking, it's one accept set Fi for until subformula of phi. Good. What was phi? Phi was something of the form, in our case, what was it, A and next A until, I think, A and not next A. Yeah? What are the until subformulas? There is only one until subformula. So in my example, K equals 1. This means in particularly, if you give me a formula that has no until subformula, K is 0. Sounds a bit strange, right? So if you give me a formula like this, no until formulas included, set of accept sets, empty set. Now remember, when does a generalized Büchi automaton accepts? If for all accept sets something holds. For all over an empty domain means all runs of the GNBA that you construct for this word, for this thing, are accepting. Yeah? Sometimes confusing, but this is the way it is. But in our case, we have K equals 1. Good. So how is this defined? This is defined as follows. So take such an until subformula. The rule says, okay, this F is the set of B's, so the set of states, such that the until formula you are considering is not in there, or phi 2 is there. Good. So go to my table. This was the table. Yeah. The condition says the until formula is not there. Yeah. Or phi 2 is there. So what does that mean? Here we have that F of the entire formula phi are all states for which phi is not included, right? Which is B0, B1, and B4. Yeah, those are there because phi is not in those states. Maybe we have to extend this. The second part of the definition says, okay, psi 2 is in B. That means phi 2 is in B, but it's only applicable for B2. And that's there, so I have to add B2. And this is there because phi 2 belongs to B2. So we have 4 accept states. If you allow me to draw them as double circles, this is going to be an accepting state. B1 is an accepting state. B4 is an accepting state, and B2 is an accepting state. And after all this work, this is the generalized non-deterministic Buggy automaton for this formula. What is the intuition behind this definition of the accepting sets? Yeah. It's basically the idea that you would like to get an infinite run accepting this until formula. And what I'm going to do in the next lecture, that takes at least half a lecture, is to prove that exactly this definition is the correct one. And that actually, indeed, we get the theorem that says that this automaton accepts all the words that are satisfying the formula phi. Good. Here is another example, just to his next A. This has 4 elementary sets. This is something that you can construct yourself. Next A means no until subformula, which means no accept states. Yeah. Initial states are those that contain next A. The transition relation, there are some examples here. So for instance, there is a transition there. The only atomic proposition is A. This contains A, so it only has outgoing edges labeled with A. And then it goes to those states that are basically what you see here. If next A is in B, then you have to go to the states where A holds. This is a state that satisfies A, that satisfies A, so therefore there are A transitions to both states. Yeah? That's the way to see this. Similarly here, this is the case that I already showed you with the negation. So this means these are labeled with empty set, and they go to those states. And if you consider this, go further, set of accepting states, there are no accepting states, so all infinite runs are accepted. And actually this is the automaton you have in the end. Now take a run like this. It's clear this run satisfies next A because in the next position A holds. What is now an accepting run for this word? Yeah, and that's the construction I showed you before. So this is the state that actually corresponds to this first symbol. It's the input state over here. Now there is an A. So what happens if I have an A? Well, A and next A, that means actually that you go to this transition. Then you go to this transition and so forth, to that state, to that state. This is a run. All runs in this automaton are accepting because the set of accepting states is empty set. So this is an accepting run for this word. Yeah. Next lecture we will prove that indeed for all runs satisfying this formula, there is an accepting run in general of the whole construction. So that's the correctness proof of Vardy-Wolpe. Thanks for your attention. Hope to see you back on Friday.